Chapter 5, Ohm's Law. Again, we should like hit a gong, ring a bell, ring some chimes. Ohm's Law. Ohm's Law has more of an effect on being able to predict the behavior of electricity than really anything else. Does anybody know how predictable the behavior of electricity is, percentage-wise? We were talking about tolerances last chapter. Anybody know how accurate we could predict the behavior?
I'll say 100%.
100%. It's a bold statement. It's absolutely correct. 100%. You use Ohm's Law, you could predict with 100% accuracy what's going to take place inside a circuit. It's pretty powerful. It's a pretty powerful tool, especially when you're going to be paid to go out into industry and fix broken electronic equipment. You got this tool working for you, you got something. After completing this chapter, you're going to be able to identify the three basic parts of a circuit, identify three types of circuit configurations, describe how current flow can be varied in a circuit, state Ohm's Law with reference to current, voltage, and resistance. Solve problems using Ohm's Law for current, resistance, voltage, and series parallel circuits. Describe how the total flow differs between series and parallel circuits. Describe how the total voltage drops differs between series and parallel circuits. Describe how the total resistance differs between series and parallel circuits. State and apply Kirchhoff's current and voltage laws. And verify answers using Ohm's Law with Kirchhoff's law. First of all, electric circuits, or the path that current follows, is called an electric circuit. All circuits consist of, and this is important, and it sounds really basic and it sounds very simplistic, but I'll tell you what, knowing this helped me on my worst day of my career as an electronics professional. Because it's so easy to get turned around and lose track of what the problem is. And if you could get back to basics, you're always going to do well. The basics are all electric circuits must consist of a voltage source, a load, and a conductor. The voltage source is the source of your electric energy. It could be any of those 6 different types that we talked about last week. The load is what converts one form of energy into another form of energy. An example of an electric load would be a light bulb, a motor, a heater. It converts electric energy into light, heat, motion. A conductor. A conductor, electrical conductor, transfers the energy, the electric energy, the current, from the source to the load. You have to have those 3 parts of a circuit, or it's not a circuit. I'm going to add 2 other optional parts that are not in the book. The other optional device, most circuits have them, not all do, is a controlling device. A simple example of a controlling device is a switch. A simple example of a complex controlling device is a microprocessor with 1.9 billion transistors on it. So you see, that's where we're going in this course, by the way, from one switch to 1.9 billion switches in a microprocessor. Controlling device is used to control the flow of current in the circuit. And the 5th optional device that you could have inside a circuit is a protective device. An easy example of this is a fuse, a circuit breaker, a fusible link, a thermal circuit breaker. These are all examples of protective devices. So, On my worst day of my career as an electronics professional, it involved a nuclear submarine someplace we weren't supposed to be. And it involved, unfortunately, my equipment that I was responsible for. There were 3 of us that were responsible for that system. Big system. $16 million system. And that was like in 1982 dollars. Expensive. This system was sold to the Navy, and it was designed with what was called graceful degradation. That means bits and pieces could fail, and the whole system would keep up and running. That's what the vendor told the Navy when the Navy bought the system. So here we are someplace we're not supposed to be, doing stuff we weren't supposed to be doing, and it was showtime for my equipment to do its thing. Didn't work right. Didn't work at all. As a matter of fact, it was totally down, 100%. And the captain, like, Mr. Grenick, how can this be? The system was designed with graceful degradation. It should never be 100% down. Well, Skipper, it's like this. It's totally busted. I don't care what you got to do. I want you to fix it. And we literally worked on that system nonstop, 3 days in a row. Stayed up. Popping no-dos, drinking coffee, just working on it, working on it, working on it. 2 other guys, they finally gave up. They're like, we just cannot fix this. It's not fixable. It just cannot. We can't bring it back from the dead. Me, I went back to these basics. It's an electronic system. It's made up of nothing but circuits. Circuits have a voltage source, they have a load, you have interconnected with conductors, have controlling devices, and I have protective devices. Is something not doing what it's supposed to be doing? It's got to be. That's what's causing the problem. It's narrowing it down. And I stuck with the problem. I ended up fixing the problem, saved the day, whoop-de-doo, I basically did my job and fixed the equipment. But I had to take a couple steps back and say, here's a $16 million system. Fills half a room with equipment racks. None of it works. Can I verify the voltage sources for everything? Can I narrow it down and say, this stuff's not working, but this stuff is working? Can I look at the loads? What's not working? What's not converting electric energy into the form of energy that we need to be getting out of it? So if you know all of these systems, then you're going to be an effective troubleshooter. But always go back to basics. Okay, God forbid you get out of class tonight, go out to your car out in the north parking lot, turn the key, and you've got an electrical problem. If you do have an electrical problem, approach it like this. Do I have a good source? Is my load functional? Is it the interconnects? Can I prove that the interconnects are viable? Is it a controlling device? And to be honest with you, in this day and age, most of the problems we encounter are controlling devices. Okay? It's not a simple switch, toggle switch. That was easy to troubleshoot. I do a lot of traveling. I forgot what brand car it was. I got the rental car. I flew in, it was the East Coast, and I'm there late at night, and I got in, and I'm like, I couldn't figure out where to put the key. Where do I put the key to start the car? There was no place to put the key. And I'm looking at it. You know, I got a little flashlight, and I'm looking, there's no place to put the key. I didn't need a place to put the key. The fact that the key was on my person was good enough for the car. You just hit the start button. Ooh, it started. All right. So the controlling device there was the fob, right? RFID talking to the computer saying this is a valid operator to be inside the car to operate it. Kind of a complex controlling device, but a controlling device nonetheless. And of course, protective devices. And sometimes wacky stuff is done with protective devices. I was working on my TiVo about a month ago. I had problems with my TiVo, and I've got an older TiVo. It's a direct TiVo. So it's got 2 dual receivers, so I could record 2 shows and watch another show. It's non-HD, because I don't have HD. I don't want to pay for HD. I'm a cheapskate. Okay? Feed my nice plasma screen. High-resolution plasma screen with my basic signal. It's great. It's great. It's all good. My TiVo crapped out. Okay? So all the TiVo is got a hard drive in there. So I got a new hard drive, I configured that and everything, and I was just through putting it together, and something happened, and I heard a pop, and all of a sudden TiVo wouldn't fire up anymore. And I'm like, oh man, if this thing is dead, I don't want to go out and buy a new DirecTV DVR, and it's a higher, I'm grandfathered into paying the older TiVo value, and plus, quite frankly, I don't know if any TiVo users here, TiVo's the bomb. It truly is, because it could do word searches and all kinds of additional stuff that a normal DVR will not necessarily do for you. So I wanted to bring this thing back from the dead, and I'm like, what the heck? I was pretty ticked off, because I already wasted a whole weekend screwing with this thing. So I'm looking through the circuit for something obvious, and I find this device, and basically it's got shrink wrap, black shrink wrap over it, and 2 leads coming out of it. And I measure across it, and I'm getting an open. I mean, I just got in there with the thing unplugged, and I'm poking around. I'm like, what the heck is this? So anyway, I unsolder it, and I inspect it, and with an X-Acto knife, I cut the heat shrink up. You know what it is? It's a fuse. It's a fuse, and the manufacturer tried disguising it by putting a piece of heat shrink around it and sticking it on the circuit board, and that's what was burned out. I found a suitable replacement that I had at home in my tin can, soldered it back in place, fired it up, I was good to go. TiVo's been working nonstop ever since. Okay? But that's a hidden. A lot of companies do that type of stuff. So that if you don't know, if you're not the authorized service center, you don't know to get in there and even check that. I've seen some companies that will encapsulate a fuse inside silicone or epoxy. You don't even know it's in there. So keep your eye open for all these basic parts of a circuit. I know this sounds basic and I'm beating it to death, but I tell you, you will deceive me in the future when you get in the lab. And it's going to be, I can't fix this. The problem's too complex. It's never a complex problem. It's usually a real simple problem. Very rarely. All of you are here. You want to get into advanced electronics and work on sophisticated equipment. The problems with sophisticated equipment are always very, very simple. Okay? You gotta follow this protocol though. So use this as a checklist. This is a series circuit. We talked about series circuits already. The most important thing for you to remember about a series circuit is that current is constant in a series circuit. The most important thing to remember is that current is constant in a series circuit. Meaning, I've got a resistor here, a resistor here, a resistor here. These 3 resistors cumulatively add up to the total amount of resistance in the circuit. This electrical pressure here encounters this total resistance and allows this amount of current to flow. This current has to travel the entire path of the circuit. That is the most important thing about a series circuit, period. The second thing I want you to remember about a series circuit is a series circuit is also known as, like FBI lingo, AKA. A series circuit is also known as a voltage divider. A voltage divider. What voltage gets divided up? The total voltage. Remember this? We call this voltage rise. How many voltage drops do I have in this circuit? 3. So voltage rise is going to get divided into 3 proportional values. The biggest resistance gets the biggest voltage drop. The smallest resistance gets the smallest voltage drop. And the resistance that's just right gets a voltage drop that's just right. Make sense? That's the series circuit. The parallel circuit, the most important thing I want you to remember about the parallel circuit is that voltage is constant across a parallel network. This is a parallel network. Here there are 3 resistors in parallel with each other. The voltage rise will be distributed equally across all 3 branches. So whatever this is, if this is 120 volts, this is going to have 120 volts across it, this is going to have 120 volts across it, this is going to have 120 volts. Kind of like how your house is wired. Your house is wired in parallel. Each of the outlets has the same voltage across them, or they should. If not, you got a problem. That's the most important thing about a parallel network. A series circuit was also known as a voltage divider. A parallel circuit is going to be known as a current divider. Because what happens to current in the circuit? This total current here gets divided here, at this node, and here. Then current gets divided here and here. The current flowing through R3 and the current flowing through R2 join up at this node and flow on to this node. This current plus this current equals total current. Series circuit, current's constant. Series circuit, also known as a voltage divider. Parallel circuit, voltage is constant, also known as a current divider. Complex circuit, well, that's got both going on. I've got current division going on here in my parallel network, and I've got voltage division going on here between this resistor and this resistance. This resistance. The best thing you could do in this circuit is label this A, node A, or in B, or X and Z, or whatever you want to label it. Give it some, I like using letters, because numbers typically equate to components. Letters I could use to, and there's no rule on this, but it works for me. So I'm going to label this node A and this node B. The resistance between node A and B is equal to the product over sum of R2 and 3. Remember that? Studied that last chapter. The total resistance of the circuit is going to be equal to R1 plus RAB. This voltage drop, RAB, plus the voltage drop across R1 equals RT. Voltage rise. And really, how many voltage drops do I have in the circuit? Really, how many voltage drops do I have in the circuit? 2. And what are they? R1 and RAB, or R2 and R3. If I say R2, it's really the same thing. R2 is the same as R3. You could argue and say, well, you really got 3 voltage drops here. You got a voltage drop here, you got a voltage drop here, and you got a voltage drop here. Well, this voltage drop and this voltage drop are the same voltage drop. It's the same difference in potential. So it really, I don't want to call it different. It's the same. Make sense? Some different circuit conditions that I want to talk about. And this is very important. I want you to use the proper terminology with me. It's part of why you're here at Lake Washington Technical College studying this stuff, is to learn to speak another language, the language of electronics. The circuit condition that I want to talk about is called a closed circuit. Is a closed circuit a good thing or is it a bad thing? Depends on what you want. Thank you. Depends on what you want. Right now, the circuit in this room for the interior lights is closed, meaning the circuit's energized and we have an appropriate amount of illumination in here. That's a good thing. If I go and operate the switch and try to open the switch and the lights won't go out, that could be a problem. That could be a problem. If you're operating an electric tool and you try to shut it off and you can't shut it off, that's a problem. Be a closed circuit is causing you a problem. I had this problem with a pressure washer. One of these $100 pressure washers, Costco special. Great pressure washer, okay, for what I do. Got a patio, I got a deck. I don't need a, 40 horsepower, fire-breathing, peel the paint off the Queen Mary pressure washer. But it's my pressure washer, and I like it. I got a lot of tools. Got a lot of neighbors that know I got a lot of tools. My neighbor Tom, he since moved. It's another story. I'll tell you about that some other time. Finally drove him out of the neighborhood. Tom's an engineer, an electrical engineer with Boeing. Hey Joe, I'm going to stain my deck. Can I borrow your pressure washer? I'm a nice guy, but I hate loaning out tools because nobody takes care of stuff like I want it taken care of. I mean, if I borrow somebody's tool, I take care of it 10 times better than my own. And if I break it, I buy it. I replace it. I said, Tom, that's fine. I'll loan you my pressure washer. But, only plug it in a dedicated outlet. And do not use any extension cords. Because it's right on the label. It's not that I'm that smart a guy, I just read the label, the tag that's on it. Because this motor requires a lot of current to be able to turn and be effective. You plug it in an extension cord, it doesn't get the right amount of current. Remember that whole thing, the cord gets hot. The hotter it gets, the more resistance, less current, the less current, the hotter it gets. It's a vicious cycle. So I loaned him my pressure washer. How did it work out? Oh, pretty good. Thanks, Joe. Fast forward a couple weeks later, I go out to wash my sidewalk. I plug the thing in, turn it on, and it's on. Continuously on. It won't shut off. Normally what happens, it's a real simple circuit. This switch right here on a pressure washer, one of those cheap Costco specials, what it does is there's a water pressure sensor. When the water pressure builds up, what it physically does is open the switch. So what you do in the handle, when you release the switch, you release the pressure. As soon as you release the pressure, you close the switch, you turn your motor on, the motor turns the pump on, and you're pressure washing. You release the trigger, you build the pressure up, you open the switch. Mine will never shut off unless I unplug it. If I unplugged it and it still kept operating, well, that'd be something. Keeps operating. I ripped the thing apart, and what had happened was, I guarantee you, I didn't see him do it, but because I had no problems with it, and I had it for years. He plugged it in a non-dedicated circuit, it built up a lot of heat, and physically the switch, the contacts got welded. I took the switch apart, the contacts were welded to each other. That's how hot it got. So I went to my file cabinet, opened the drawer, pulled out the manual, got the parts list, contacted the company. The new switch would be $65 plus shipping. A new pressure washer at Costco, $109. I could have it right now. The old one's in a landfill somewhere. After I cannibalized some parts off of it.
You talk to your neighbor Tom?
No, I ran him out of the neighborhood. Finally ran him out of the neighborhood. There was a chainsaw involved. And trees falling. Long story. Long story. No, actually what pushed Tom over the edge was he had problems in his basement, flooding, split level house, and water would get in. So what he did is he dug a trench around the entire foundation of his house. And then what he's going to do, he's going to put a treatment on the outside concrete. And then he was also going to backfill it, put in drainage and everything. So he had this ditch dug. It was a lot of backbreaking work. He did it all by hand. Got to respect that. But it took him forever to do it. It took him years to do it. So I used to accuse him of having a moat. It's like, Tom, what's the deal with the moat? So anyway, again, I had a buddy of mine over, and it was the wee hours of the morning, and we were enjoying some libations and some cigars. And actually, my buddy, who's got my sense of humor, he's like, "Hey, Joe, is that Tom's moat? What's up with that? Doesn't he want that thing full?" I'm like, "That's a good point. Why have a moat if it's not?" So anyway, we turned on his garden hose and started filling the moat, and then we're just laughing and like busting a gut. And then Tom came out, and he's pretty freaking ticked off that we're filling his moat with water. I mean, he woke up to the sound of running water. Like, why is water running in my house? And, hey, man, we thought we were doing you a favor by filling your moat, He was out of there within 6 months. Open circuit, is this good or bad? Depends. Depends. On my pressure washer, this would have been highly desirable. When pressure builds up, it opens the switch, interrupts the flow of current to the motor, right? Another circuit condition is called a short circuit. Have you all heard of a short circuit before? God bless my wife, but she's been my wife now for a long time. And I've been in this industry since puberty, so, you know, hanging out with a guy that teaches electronics and does electrical stuff, you'd think something would rub off. Constantly, I get a call, and it's kind of like, the blender's not working. I think it's got a short circuit. And I'm like, holy crap, you tell short circuit to me, I'm like ready to call the fire department. I mean, short circuit is like what you see in Star Trek when they get hit by a phaser, you know, I mean, that's a short circuit. That literally is what a short circuit is. A short circuit will cause an electrical fire. And then on further probing, well, what exactly is the blender doing? Well, I plug it in, I hit the button, but nothing happens. Oh, you mean it's an open circuit, not a short circuit. Big difference. The majority of household appliances that I've encountered that have failed because of an open circuit condition. That's where nothing works. Now, you got to be careful because sometimes a short circuit will cause a protective device to open and render the piece of equipment dead. So you've got to get in, and like that DirecTV, that was dead. That was open, intentionally. I found the open. It was that fuse with heat shrink around it, trying to disguise it to make it look like a fuse with heat shrink around it. Make sense? So keep that in mind. Open circuit, short circuit is always bad. There's never an intentional reason to short anything. Current flow in a circuit can be varied by changing the voltage applied to the circuit. As voltage increases, current increases. As voltage decreases, current decreases. And also changing the resistance in the circuit. As resistance increases, current's going to decrease. So these first values, we call these directly proportional, right? If voltage increases, current increases, directly proportional. Voltage decreases, current decreases, directly proportional. Resistance increases, current decreases, inversely proportional. Now, in the beginning, when Ohm gave his sermon, I don't know if it was a sermon, Ohm's Sermon on the Mount. Somehow I think I'm getting my history messed up. This is what Ohm said. I think this speech was given down at the Kingdom. And he was at the Kingdom, and he got up, hello, hello, hello. This is, I'm the happiest man alive. Because I know, Ohm's law. Y'all ready for this? E is equal to I times R. And the crowd went nuts. 45,000 people on their feet. Ohm's law. Ohm has spoke. Actually, I think I'm getting my history mixed up a little. I don't think it went down like that, quite like that. So this is Ohm's law. This is what Ohm really said. Voltage is equal to current times resistance in the circuit. And of course, instead of the letter E, we could use the letter V. V is equal to I times R. Now, remember that trick that I showed you with the triangle? T in the center? Let's put this in that. V, I, R. So now you've got all the other variables. If I ask you how much resistance is in there in a circuit, you cover R up, it's voltage divided by current. If I ask you how much current is there in a circuit, you cover up the I and you say it's V over R. If I ask you how much voltage is there in a circuit, it's I times R. So by knowing that one formula, you can figure out all the other algebraic manipulations of it. Does that make sense? So in essence, that is Ohm's law in all of its variables, or variations, I should say, algebraic variations. So you don't even need to be a math whiz to be able to do it. Ohm's law states relationship between current, voltage, and resistance, or I is equal to E over R. or E is equal to I times R, or R is equal to E over I, however you want to look at it. But, in the beginning. It was V, or actually E is equal to I times R. 45,000 people on their feet, applauding. The man with the beret. I don't know if he wore a beret or not. If I was Ohm, I'd wear a beret. Some of the algebraic formulas, if you will. And when I say that, I know there's some people in here that cringe, like, oh, I got to know all this math or whatever. All this is a recipe. That's all this is. By laying it out like this, it shows you how it needs to be laid out to explain the behavior. In a series circuit, the same current flows throughout the circuit. Total current is equal to the current through resistor 1 plus the current through resistor 2 plus the current through resistor 3, etc., etc., etc. It's a fancy way of saying current is constant in a series circuit. Total voltage is equal to the voltage drop across 1, across 2, across 3, etc., etc. This is a fancy way of saying a series circuit is also known as a voltage divider. Total resistance in a circuit is the sum of the individual resistances in a circuit. This is a fancy way of saying you got to add it all up. Resistance is additive in a series circuit. In a parallel circuit, total voltage is constant across the parallel network. That's this formula. Down below, total current is equal to IR1 plus IR2. This says that a parallel circuit is also known as a current divider. Oops, that is. That's another formula, right? The reciprocal of the sum of the reciprocal of the resistances equals the reciprocal of the sum of the reciprocals equals the total resistance in the circuit. Because when we add resistors in parallel, what are we doing? We're actually adding up the conductivity of the individual branches. To determine unknown quantities in a circuit, you can kind of use this as a checklist. Draw a schematic of the circuit. You got to start off with a schematic of the circuit. If one has not been provided to you, you need to draw one. Okay? Because just troubleshooting circuits off the top of your head doesn't really work well. Got to be looking at the big picture. Pun intended. Label all known quantities. Sometimes you may need to get these known quantities from manufacturer data sheets. Solve for equivalent circuits. Solve for equivalent circuits. Redraw the circuit. When I say redraw the circuit, remember like when we were dealing with a parallel network, two resistors in parallel with each other? You could redraw that circuit and just show one resistance. Two resistors equals one resistance. I could do a simplified, you want me to do a simplified drawing of my car electrical system right now? Want to see this? Battery. Car. And to be honest with you, I'm not being silly, I could redraw every circuit on my car and come up with an equivalency, and this is what it is. And I'll tell you what, if you go out to your car and you turn the key and there's nothing, and you open the door and the dome light doesn't come on, nothing works in the car, and all of a sudden, this is exactly what you've got, and there's an open in this circuit, and it's a pretty big open, or your battery's dead. I don't think your whole load is dead. It's like, oh my goodness, all my load is dead. I got to replace the load. Save the battery, but we're gonna. You know what I'm saying? Doesn't work like that. But do you see the power of troubleshooting like that? What's working in the car? My car's dead. What do you mean it's dead? It's a conversation with my wife. The car's dead. What do you mean it's dead? It's dead. When you turn the key, does it click? No. When you open the door, does the dome light come on? No. Oh, it's dead. But you got to ask those questions because it's different. When you open the door, the dome light comes on. But you turn the key, does anything? Do you hear a click or anything? Immediately you're troubleshooting. You're narrowing it down to what circuits perhaps could be faulty. So redraw to simplify. There's another big law out there. It's Kirchhoff's law. G.R. Kirchhoff extended Ohm's law with two important statements. Kirchhoff's current law: the algebraic sum of all currents entering and leaving a junction is 0, equal to 0. Kirchhoff's law is kind of like this. Everybody know the intersection down here at the bottom of the hill? Okay. Let's say that you're a traffic cop and you're directing traffic down there in the center of the intersection. Okay. And you got 3 cars coming at you this way, and you got 5 cars coming at you this way. In a few moments, how many cars are going to be going away from you? 8. Because 3 are coming from one way, 5 are coming the other way. You know, chances are cars don't come and then, oh, we were just kidding, we're going to back up. You know, I mean, I've seen them do that down here. But generally speaking, you know, 3 plus 5 equals 8. Pretty profound, isn't it? That's what Kirchhoff came up with. And he made the textbooks. You laugh. His name's in the textbook. My name's not. That's Kirchhoff's current law. And what Kirchhoff is saying is, again, the total current entering has to exit. And it's really a profound troubleshooting tool. Because what you could do is I say, I've got 3 amps of current flowing at me, and I've got 8 amps flowing away from me. What does that tell me? I must have 5 more amps coming in from another direction that I'm not aware of. And there's only one other circuit, so I must have 5 amps. And I tell you what, you could take that information to the bank. It's a law of physics. And it's so powerful in troubleshooting. It's extremely powerful in troubleshooting. There was a guy that was in my division, one of our techs in the Navy. Goofy guy. I'll tell you some stories about him and his wife in the future. But this dude, it just, you know, every day was a mystery what you'd see this guy into. So military equipment is put together really, really, really well. And we didn't have cordless screwdrivers, so you used to have to take stuff apart by hand. So I come in and I'm like, you know, what are you working on? He's like, yeah, we got a problem with this unit here, and I want to take this current reading, you know. And, you know, in order to take a current reading, I got to open the circuit. So you're going to remove this access plate here with 64 screws, and you're going to remove that. You're going to get in there and take that reading. You know, why don't you use this here, which is called Kirchhoff's law, okay? You got this amount of current going this way, this amount of current coming in, and the unknown is what you want to measure here. You can use Kirchhoff's law and determine with 100% accuracy how much current's flowing through that point. You don't have to take the panel off. You don't have to remove the screws. You don't even have to use a meter. You could use math. Put the meter down, math, solve the problem. And to be honest with you, these are the technicians that I look for. These are the technicians that I want to hire. If you start the troubleshooting process with the manual, and then you're going through tracing, redrawing, applying these principles, these laws, before you go ripping into stuff, you're going to save yourself a lot of grief. A lot of grief. It's like go to work for Boeing. Boeing builds big airplanes. On the tail of their airplanes, they put a light that blinks so other airplanes don't hit their airplane when it's flying. You know, I'm not making this stuff up. It's kind of like the light doesn't work. Well, let's get a man lift and get up there and take it apart and whatever. You get a man lift, you get all harnessed up, you know, you're 5 stories in the air, you're manipulating the controls, and all of a sudden, oops, you put a dent in the rudder. When you could have done some troubleshooting probably through an access panel down below using Kirchhoff's law. How much current do I have flowing up there? What's going on? Then make some determinations. Is it really essential for you to get up there and take that assembly apart? Get a man lift, harness yourself up, run the risk of plowing into the rudder accidents happen. So always look at that kind of stuff. Is there an easier way of going about getting the reading that I want? That's the power of Ohm's law. That's the power of Kirchhoff's law. Kirchhoff's law also has a voltage application. And Kirchhoff says the algebraic sum of all voltages around a closed circuit equals 0. This is a fancy way of saying voltage rise equals voltage drop. And you know how much you're left over with? 0. We talked about this last week, didn't we? We talked about this last week. If you put 12 volts in, how many volts are going to get used? 12. If you're troubleshooting and you can only account for 11.5 volts, that half a volt is somewhere that it doesn't belong. You got 120 volts are supposed to be coming out of these outlets. If you plug it in, you only get 98 volts. Something's wrong. If you could go to that box and prove that you got 120 across each leg, but you go to an outlet in your home and you get 98, something's wrong. You find where the missing voltage is, you find the problem. So again, does this sound really basic? What goes in must come out. It is. But I'll tell you what, when you get to industry, you'll deceive me. You're going to get your head all, wow, it's complex. I never worked on one of these before. Oh, sheesh, it's got to be something really, it's got to be the flux capacitor must have failed. You know, and I missed that day when Joe talked about the flux capacitor. No. Keep it basic. Keep it basic. The fundamental parts of the circuit, the source, the load, the internal wiring, the controlling device, the protective device. You got to be able to prove every one of those parts, functional parts, is functional. And how are you going to learn how to do that? In the lab, by doing your labs. Theoretically, how are you going to come to appreciate that? By attending a lecture and doing your written assignments. Because that's what this industry is about. It's about the written theory, which is kind of cool. Some of you had back-breaking jobs in the past. Okay? I never worked a hard day in my life. Actually, I did, but it was all mental. And I'll tell you what, there were days working on my system. That's the other thing, too. You know, that's one of the reasons that we all try to treat you as professionals here in this program. When you go to industry, you're going to be professionals. If your equipment ain't broke, they don't care what you're doing. But when it's broke, they expect you to be there bringing it back from the dead. No questions asked. Well, I'm a union guy, and do I get time and a half? Fix the freaking gear. Get it up and running. That's all they care about. And actually, there are some union maintenance jobs that, you know, do pay you well if you've got to put in that overtime. But generally speaking, this is where you make your money. This is the most, I tell you what, I'm taking a lot of time with this chapter. This is one of the most important chapters of the book. It's one of the most important chapters of this entire program. I could talk for a week about just this chapter. And you know what the beauty of it is? You've all been here. This is your third week in this program. You understand what I'm saying? Do you understand what I'm saying? The message isn't going to get any worse. It's not. The most complex electronic systems could be rapidly troubleshot, keeping these fundamental skill sets in mind. Ohm's law, Kirchhoff's law, 5 basic parts of a circuit. Is my source good? Is my load good? Is it the interconnects? Can I prove that? The other thing you got to do as a technician is just pay attention to what can you check quickly. What can you check quickly? Again, like my former esteemed colleague on the submarine, Mike Wyrup was his name. Wyrup, weird name. Okay? He'd be the kind of guy like, well, you know, I think it's the wiring, Joe. I want to do continuity checks. I mean, you're talking these big multi-pin connectors, and you're going to disconnect, check the continuity. It could take months. You really think that's the problem? You really think a wire like broke in the middle of the night behind that equipment rack? You know, I don't think so. I think it's, you know, maybe something like controlling device. Have you tried reloading the software? You know, the version of software that we have in that safe. Why don't you try reloading the version of software? Controlling device is what I'm thinking, right? Reload the firmware, software. Reboot the system. See how the problem manifests itself. Oh, Joe, the most amazing thing happened. reloaded the software, started working. Wow, good thing you didn't like take, 6 months and check the continuity of all them wires in the back of the equipment rack. What would the odds have been? In summary, the electric circuit contains a voltage source, a load, a conductor. The two optional ones, controlling device, protective device. Don't second guess those. Hey, want another troubleshooting hint? Another type of protective device? It's called a resettable fuse. Resettable fuse. A lot of consumer electronic products, DVD players, VHS players, stuff like that, tuners, TV tuners, have these resettable fuses. And a lot of times what happens is the device will not work. So it's kind of funny. My family, they all know, Joe in the family, he's the electronics guy. You got a problem, and they always call me with the problem. So it's amazing how many things I've fixed from afar. They tell me what the problem is, and a lot of these have been with DVD, VHS players, things like that in the past. So, well, what I'm going to have you do is I've got a ritual that I'm going to go through here on the West Coast. Okay, I want you to unplug that device, okay? And what's the most comfortable chair you have in the house? I want you to remove it and put it in the most comfortable chair of the house overnight. And I've got some rituals and some telepathic, things that I'm going to do. And then I'm going to call you back in the morning and let you know when I'm done. Okay, and I'll go plug it in. Holy cow, it works! How did you do that? It's all about chi. Okay? Freaking resettable fuse. For whatever reason, there was a glitch that tripped that. You got to unplug it, totally discharge the whole unit, plug it back in. It reboots thinking it's back at the factory the first day it was ever made. Problem goes away. You got to make sure you give it overnight to be able to do that. So I've brought back countless. I've had a lot of people come in here, colleagues. Hey, Joe, my amplifier, this amp doesn't work anymore. You could have it if you could fix it, okay? Because I went out and bought a new one. I figured this thing is toast. I go plug it in, it works. By you unplugging it, you fix. I don't even go into it with people. Well, you'd be surprised the amount of stuff that you could fix by simply unplugging it for 24 hours, plug it overnight, not even 24 hours, plug it back in, you're good to go.
Why does it take time? Why wouldn't it be instantly?
Because these resettable fuses, there's a time delay before they're actually solid state devices, before they physically reset and allow the circuit to function properly again. So you want to get it back to that neutral state of when it left the factory. I don't know, in mobile audio, did you encounter any of that stuff? Where by disconnecting it for a period of time would fix the problem?
Yeah, I mean, when if you did a hard reset, touch positive, negative together, make sure the circuit's completely unenergized. Airbag lights, some control systems. If you did a hard reset, would do that.
Okay.
To make sure that everything dissipates inside. So the fastest way was to.
Yeah, and that's the other thing that you can do even with like a DVD player. If you just not unplug it, make sure it's unplugged, and then keep the leads shorted together, then that's a kind of a fast track. But still, there are some capacitors we'll talk about in the future, store energy in the form of an electrostatic field that may keep stuff alive for a considerable amount of time. So, flux capacitors. Current path. We talked about series circuits, parallel circuits, and complex circuits, series parallel circuits. We talked about current flow, negative to positive, varied by changing the voltage or the resistance. We talked about Ohm's law. And also determining unknown quantities in a circuit, as well as Kirchhoff's law. For current is constant in a series circuit. Ohm's law. All the current entering a node must exit the node. Kirchhoff's law. Powerful, powerful stuff. Prevents you from removing 64 screws by hand to take one reading. He used to think I was an a-hole. This here is Kirchhoff's law, I stayed awake during that class. You could use this here tool to prevent yourself from removing 64 screws. Chronic, you're a freaking jerk. No, I'm not. I think the guy that's removing 64 screws and then's going to strip the screws, okay, break the heads off. That's another story. There was a dude, a local company, can't make this stuff up, okay, broke heads of screws off. The product's ready for shipping, got freaking instant glue, glued the heads back on. First time it was out in the field and I took a panel off for maintenance, snap, snap. What the heck is this? What is that on there? They look at it. It's like, this is instant glue. Who worked on it last at a company? Why'd you do that? But, well, I didn't want to get in trouble. You're out of here. You know, that instant. You can't make stuff like this up. Try to avoid it. Questions?
Electricity is a theory, right?
Yes, and that's basically what we're studying is the theory.
Ohm's and Kirchhoff's laws rather than theories.
Laws of physics. We have proven that although this is theory, these are laws of physics. Voltage, the relationship between voltage, current, and resistance, the relationship between voltage, current, and power, Kirchhoff's laws, they're laws of physics. We know that we could prove with 100% accuracy that this is how they behave. Mr. Graham.
Also, in science, generally, a theory is something that is provable almost to an infinitesimal degree, and a postulate is something that's unproven.
Very good. Thank you. Okay, hey, before we wrap things up, because we got another chapter to do, okay? But fortunately, one of the reasons that I took this amount of time here is this other chapter is not a chapter that I am going to lecture on. It's another chapter that you've got to watch some videos on. There are 4 videos. When you go to the Google site, it's going to say, follow this link to watch test equipment videos. Okay? And there are 4 videos that I want you to watch. And you're responsible for the information. I think all of you kind of figured out that I'm the kind of guy that likes lectures. Okay? I like to have fun with lecture. Hopefully you're not falling asleep during my lectures. But I like lectures. And it gives me quality face-to-face time with all of you. However, that being said, I'm not the smartest guy, but I know that a picture is worth 1,000 words. So if I could have you watch a 15-minute video, that's a lot of frames. That's a lot of pictures. That's a lot of data. More time than I have to preach to you about this stuff. The 4 videos. The first video is going to be a basic introduction to digital multimeters versus analog meters. Okay? The analog, when I speak of analog, this is what I'm talking about here. Kicking it old school. The digital meter is going to be based on a Fluke 70 series meter that, quite frankly, all meters are really measured against. The second video is going to talk specifically about how to perform resistance and continuity measurements using an analog meter and a digital multimeter. Resistance and continuity. The third video is going to talk about measuring current and voltage. So by the end of those 3 videos, you're going to know how to measure resistance, current, and voltage. If you know how to do that, let me tell you, you got it going on. You got it going on. Because those are 3 of the big 4 properties that all of this is based on. So these are very, very important videos. One of the reasons that we have them in videos and uploaded is so that you can watch over and over again to make sure you understand exactly what the process is. So by the time you get into the lab, you can apply that. Very, very critical. Like how to defuse a nuclear bomb. You know, you want to get it right the first time. Okay? The 4th video is produced by Fluke Corporation. How many of you know about Fluke? Okay, Fluke is the real deal. The real deal. Expensive, local company. John Fluke. John Fluke, former submarine guy. Right? Got to support his product. He was before my time. But yeah, John Fluke is a former submariner. they produced this video, and it's a drama, not a drama like, oh, I can't believe he's going to test the voltage. You know, it's got a story behind it. There's a kid who's working on the job, and he blows up something, and his boss is like, you know, you need to go out to the community college and talk with the electronics professor. And basically, it reviews how to perform basic measurements, resistance, current, and voltage with a Fluke 70 series DMM. That's the 4th video. So all of the information in those videos is testable. The link is on the Google sites. You can watch it in the privacy of your own home. You can watch it on these machines, but that is what we are doing in lieu of this chapter on test equipment. Does anybody have any questions on anything that I covered tonight? Yes?
So you just go to Google and type in something?
No, the Google site. It's the sites that were in the syllabus.
Oh, okay.
Okay? This right here, if you go to that Google sites, the electronics, LWTC electronics, you're going to see a link in there. Follow this link for test equipment videos. You click on that, and then it brings you to some server in Peru that we've uploaded those videos to. We got stuff all over the place. But you know what the alternative is? You got to sit here and watch it all. Okay, we've really tried. I got my TAs working very, very hard to get as much stuff as we can uploaded to the web so that you could look at this stuff morning, noon, and night. Any other questions on anything in general? Okay, make sure you get that video watched over the next 24, those videos watched over the next 24 hours.